Okay, good afternoon, everyone. So today I'll be talking about a project that was done with Chandan, Abhishek, and Anupam, and the title is "Jamming in a System of Persistent Active Particles in One Dimension." So active particles are particles that have associated with them some self-propelling force that tries to constantly accelerate them. Persistent because these active forces in my system doesn't change with time. I mean, both magnitude and direction remain same. And jamming is a kind of transition from a flowing to a rigid state, which is characterized by mechanically stable clusters. So as we shall see even in our system, so we dynamically kind of evolved to a jam state in which there are multiple clusters formed, which are stable in the sense that the active forces are balanced by contact forces between those particles. So first I'll talk about the model a bit, and then we'll see what the goal of this talk is. So we take n identical overdamped particles. Mind you, these are active particles, but also overdamped, of diameter some sigma on a ring. So we have some soft propulsion that prevents crossing between these particles. So we take a harmonic interaction, which when the particles are within distance sigma, they experience this. And each particle carries a persistent active force, either +1 or -1. I mean, in an initial configuration, it's randomly assigned. But with a constraint that sum of all these active forces on all particles is 0. So what this does is, this fixes the center of mass of our system. You can solely focus on the formation of clusters in the system. So on your screen right now, is a space-time plot of how such a system evolves. So on the x-axis, you have this position, and the y-axis, you have time, and each line is basically a world line of these particles. You can see them forming these aggregates, which become slower because of momentum conservation. And in the end, you have two very slow clusters joining to form one big cluster, which comes to rest. So in this example, you end up in a single cluster. You could have multiple clusters as well, depending on your initial active force configurations. So the goals for this talk would be, the first we try to analyze these steady state clusters, basically things like how the contact forces on these clusters, if they have a good distribution, and also things like how much time it takes to go to this jam state. Okay. So firstly, on your screen, on the left, you can see one such stable cluster of 8 particles. So each arrow on these particles show the active forces on each of these particles, and the F1, F2, basically Fk, is the contact force between the kth and the k plus 1th particles. So for this cluster to be at rest, we need mechanical balance, which gives us an expression for Fk. And as you can see, Fk is just the summation of all active forces up till the kth particle. Now, for this to be one single cluster, contact force between all these particles has to be greater than 0. And what that tells us is, taking inspiration from this, we can actually map this active force configuration to a lattice path kind of diagram, where each +1 active force is given by a jump on the x-axis, and each -1 active force is like a jump on the y-axis. So for this active force configuration, we have this lattice path. And what Fk greater than 0 tells us is that if you draw such a path, this can never cross or even touch the red line, which is the x equals y line. Because if it does, then you just have Fk equals 0 and the cluster loses contact. So using just this mapping, one question that we can first answer is that if I give you n cluster, how many possible active force configurations are actually valid for this? And that would just be counting the number of possible paths that go from 0, 0 to n by 2, n by 2 without ever touching or crossing the red line. So this is just a combinatorial problem which you can solve using a so-called reflection principle, something I won't go too deep into right now. But okay. So the next question is contact force distribution. So let's say Fk, you want a probability that Fk takes a particular value. For the same thing, you can also draw this lattice path diagram for a single cluster. And I point out a point, so A, comma k minus A, where the total number of steps I have taken is k, and hence I'm at the kth bond right now. And the possible value of Fk, the value from this diagram would just be the sum of these active forces, which is just 2a minus k. And as you change A, so basically what you have is at the kth position, you have the different values, possible values for the contact forces. And the probability that Fk takes a particular value 2a minus k, where A you can vary, is the total number of paths that start at 0, 0, go up till n by 2, and cross your A, comma k minus a without ever touching or crossing the red line again. And that is something you can calculate. One of the, I don't give the complete expression here, but one of the results is that if you take a n cluster and look at the midpoint, then the most probable force would scale as something like root n. Now, the next question I want to address is that about dynamics. Let's say you start at a particular initial active force configuration. Can you say anything about how many clusters would be formed at the end after you reach the jam state? So for that, I want you guys to observe one thing, that let's say initially you have some active force configurations for all the particles. So I write that on this lattice path. So now, of course, I can cross the red line because I'm not in a stable, steady cluster. But what we see is, if you choose the step that is furthest to in the minus x direction from the red line, and if you just shift this diagram and start it from there, then you have something like this. Now you can do this shift because we're on a ring, but of course we could have, so this, if you call this this leftmost step, we could have multiple of them, and if you had that, then you would have a situation where you touch the red line, but you would never cross it. But the thing is, once you see it in this perspective, obviously, when this whole section would go on to end up in a single cluster, and here you have two such sections which go on and independently become two clusters. So all you need to do to know how many clusters would be formed in the end is just check. You may just do a cumulative sum, and wherever there's a minima, you just count the total number of minimas that are there, and that would give you the total number of clusters that would be formed in the end. So this tells us that given an initial active force configurations, how many clusters are formed. But there's this other question, that what is the probability that you get a single cluster, or let's say multiple clusters. So in order to do that, let's say I address the question, what is the probability that dynamics leads to a single cluster. So for that, we look at these kind of diagrams, where you have this path starting from 0, 0 and going up to n by 2 without even touching or crossing the red line. And you just count the total number of possible paths, but then you can obviously shift them in n ways, and those will still give you one single cluster, right? So what you do is you just count the total number of paths, multiply by n, and divide by the total number of all possible active force configurations, which is just 2nc, which is an nc n by 2. And remarkably, what we see is that dynamics, in half of the times for large n, the probability that dynamics leads to a single cluster is almost half. So you can do the same kind of calculation for multiple clusters as well. Let's say you say that I have k clusters of sizes like A, B, C, and so on. So you can just do the path counting, and then you have to do the shifting. But for multiple clusters, you have to take into account some symmetries that might arise. Maybe you do smaller number of shifts and you get to the same paths again. So that is something you have to take into account. Expression I don't give here. Okay, so addressing the next question, that how much time does it take for the system to reach those jammed state? So the thing we're focusing on is the mean jamming time, that you take a fixed system size and you just calculate the mean jamming time. And numerically plotting this, we see that the mean jamming time, at least looks like something like a power law with some with a power something like 1.67. Now we want to actually try to do some analytics and verify if this actually is the case. But in order to simplify it, we check a few things. That if you saw, the half of all possible initial configurations actually led to a single cluster. And the second highest weighted situations were that in which you get two clusters, but one of them is like order n, is like huge. So we thought that maybe if you just look at single cluster, could we get a similar scaling? So we actually saw that you can just go to the single cluster configurations, and not just that, you can just look at the last collision in them. So which is like a factor of the total time that it takes to jam, because it's the last collision that takes the majority amount of time, because clusters that just get slow, and so that is something you want to look at. So let's say we are looking just at last collisions of those initial configurations that will lead to single cluster configurations. Then in that case, you just need to calculate the average of the inverse relative velocity between those two aggregates that would be approaching to form one single cluster. And if you numerically simulate it, you will just get n to the power 0.67, which looks fine because then multiplying it by distance would give us the total time, and distance would be order n in such situations. So our question is, can we calculate this average of inverse relative velocity between these two moving clusters? So okay, so what we take is, we take the situation we have a smaller m cluster here and the n minus m cluster, these two are approaching, and what we consider is this smaller m cluster has k positive active forces, and k obviously has to be greater than m by 2 because this is moving on the right hand side. So taking just this is enough because the other situations would just be symmetric and would give us the same average. So using the fact that we have k positive active forces, so we can write the v1 velocity of the m just in terms of k and capital M, and then the relative velocity as well becomes as a function of this k, m and m. Once you have this, you can write in principle your average of the inverse relative velocity as this, where you take 1 by v multiplied by the probability that this m cluster has k positive forces, sum over k, and then multiply by the probability that you would actually have a m size cluster on the left. The thing is, P of m is something that we see in numerics is basically flat. So I mean, so you don't exactly understand it, but so we assume that, let's say each m is equally likely. Then the problem just boils down to calculating what Pm of k is, which is that given m, what is the probability that you have k positive forces. So this is also a similar problem as to what we're doing initially, the lattice path diagrams again. But this time, remember, we have an m cluster that's moving with some velocity, and that has k positive forces. And what we do is, so I'll just go briefly over this region. So what we do is we look at the contact force again. So contact force has to now be greater than not 0 but something else because it's moving by some velocity. And then finding that probability is like counting the number of paths that goes from 0, 0 to k, comma m minus k. But now the red line that it has to avoid, I'll just take 1 minute. The red line that it has to avoid is not the x equals y line, but some other line that actually joins 0, 0 to k, m minus k. Now this problem is slightly more difficult than the other one because you can't do a reflection principle here because this line is probably not even passing through the grid points. So what we do is we do a continuum mapping, and this basically maps to a Brownian particle that's moving from one point to another, and there's this absorbing boundary, basically a first passage problem, but the absorbing boundary is also moving with some velocity v. And then we want to find the first passage probability to this point. And doing this, doing this whole thing, what gives us is not actually a power law, but 1 by v average looks like something like root n log n instead of a n to the power 0.67. So initially, so what our claim is that initially it looked like a power law, but it was difficult to distinguish between a root n log n and a power law. But you can see on the right hand side, so if I just do 1 by v average by n to the power 1 by 2 versus log n, that would give a root n log n kind of thing. It looks almost like a straight line. But again, log of the y-axis versus log n looks like somewhat less of a straight line. And that makes us guess, the analytics makes us guess that it's actually a root n log n, which is showing up as a power law in the region we're able to simulate. So yeah, so that basically concludes, and this is like a summary of the things, and that will be from my side. Thank you. Yes.
Questions?
Hi. Would the dynamics of jamming change if you have even versus odd number of particles?
Right. So in our case, we just assume summation f is 0, right? So we just take even particles. That is only that imposes it in itself. If it's odd, then you probably won't have these kind of. If it's odd, then I think in most cases you'll just end up in single cluster that would probably keep moving, since the summation f won't be able to be 0.
Thank you.
Just one thing. When you calculate the mean jamming time,
right?
Do you have a distribution of how the jamming time looks?
Right. We have a distribution, something I don't show here. So
okay.
it's.
I just wanted to know whether if the distribution is good enough to look at only the mean, or
Okay.
if it is flat-tailed enough that you should look at some other.
So it is actually not. It actually has a flat kind of tail, and when we actually collapsed, when we did a scale collapse on those distribution, it looked at like the peak was at least getting collapsed at some n to the power 1.5, and not 1.67. Then we thought that just check how the mean. So what we calculate is how the mean basically scales.
So
So
not looked at other typical values.
no. Yeah.
Any other questions? Not, let's thank the speaker.
Thank you.